Welcome to one more video on analog filters. In this video we'll see the first order lead RC network. We'll see the working of this lead network both in theoretical using 20 sim simulator as well as using LT-Spice. We'll see the transfer function of a first order network, which is already discussed in the previous filters topics also. This is a general transfer function. So for a lead network, what we are assuming is that let the 0 come first before the pole. So that's why we are assuming A0 by A1 happens to be less than omega naught. The position of 0 is earlier to the pole, which is exactly depicted here. So this is the 0 position, which is closer to imaginary axis than the pole. Pole is located at omega naught, whereas 0 is located at A0 by A1 away from the imaginary axis. This is the pole 0 plot, and this is the magnitude plot of the lead network. As we can see here, initially there is no slope, that is 0 dB per decade. Since a 0 comes at A0 by A1, the slope of the magnitude plot increases with a rate of plus 20 dB per decade, and then it again becomes 0 dB per decade after omega naught, because at omega naught we are going to have a pole. So this is the magnitude plot. Initially 0 dB per decade, the slope increases and then again becomes 0 dB per decade. So we are assuming let the 0 be located at 1 kilo radian per second, let the pole be located at 10 kilo radian per second. So this is the expression for the phase of the lead network. So exactly the same expression what we have it for lag network. Only thing is that we're going to assume that 0 to be located at 1 kilo radian per second and the pole is located at 10 kilo radian per second. So which will again give a maximum frequency, which is square root of fp into fz. In terms of frequency, it is 5.02 kilohertz. In terms of radian per second, it is 3.16 kilo radian per second. So this is what we're going to get. So as we can see here, when the frequency is 0 hertz, the phase will be 0. When the frequency is other extreme of infinite hertz, the phase is again 0. The phase will be a maximum of 54 degrees at a frequency of 5.02 kilohertz or 3.16 kilo radian per second. We'll see the demonstration of this in 20 sim simulator. Now we can see the 0 is located at a lesser time constant, that is at a lower frequency. Sorry, this is a bit higher time constant, 0.001, where the frequency is 1 kilo radian per second, whereas the time constant of the pole is 2 less, which will going to show the location of pole at 10,000 kilo radian per second. So let us see this in 20 sim simulator. So let us go to this 20 sim simulator and then try to locate the poles and zeros. Now we can see this is, let me edit this. This is the numerator coefficient which represents the 0. Now we can see 0 is located at time constant of 0.001, which is pretty high compared to 0.0001. Now this happens to be 1 kilo radian per second, and this represents 10 kilo radian per second. If I apply this and I say okay, let me see the pole 0 plot of it. So we know that we are supposed to get 0 first, which is closer to imaginary axis. Now you can see 0 is located at around, let me just see this. So 0 is located at minus 1000, whereas the pole is located at minus 10,000. So this is the location of poles and zeros. That's what we assume, that let omega p be equal to, so this is what is omega p, 10 kilo radian per second, and omega z is 1 kilo radian per second, which is exactly seen here. This is 1000, this is minus 10. Why it is minus means because it's on the left hand side of the S plane. So after this we will see the Bode plot of it. If you see the Bode plot of this, you can see initially it has got a slope of 0 dB per decade, and then the slope increases. So at exactly 1000 radian per second, we're going to have the 0 located. So because it is 0, the slope is going positive, and it again becomes flattened, that is 0 dB per decade, because of the presence of a pole. First a 0 comes, that's why positive slope, and then a pole comes, so that whatever plus 20 per decade will be nullified by having this minus 20 per decade, and it again becomes 0 dB per decade. And we have also seen that at a frequency of 3.16 kiloradian per second, the phase is almost minus 54 degrees. That we can verify here. You can see it's around 3.3 kilohertz. You can see this is somewhere here. This is almost 3.1 kilohertz, kiloradian per second. The corresponding phase is plus 54 degrees. So this is the phase angle is actually positive. So that's why the name of the filter circuit is called as phase lead network, because it will always give the phase of the output will be always leading the input. The maximum phase you can able to lead here in this case of pole 0 positions are 54 degrees. If you change the location of poles on zeros, we can certainly change this maximum phase, maximum positive phase is going to have with respect to the output or with respect to input. The output is actually 54 degrees ahead of the input at a frequency of 3.16 kiloradian per second. We will see the the LT spice circuit. Before that, we'll see the circuit implementation of the same thing. So let us. This is the lead RC network. So this is a circuit diagram which will give the lead phase angle. The transfer function of this happens to be. Let me just go back. Okay, this is one sec. This is a location of 0. 0 is decided by R2 into C, that is this time constant, whereas the pole is decided by R1 parallel with R2 and C. If you can see here, with respect to the value of R2, the pole position is always far away from the 0. So because it is a parallel combination of R1 R2. So if you assume this R1 to be 100 ohm and R2 to be 1 kilo ohm, with the value of C as 0.1 microfarad, we will get the corresponding pole and 0 positions at 15.9 and 1.59 kilohertz. From this we can clearly see that 0 is located at a closer frequency compared to pole. So this is what we have. So let us see the LT spice simulation of the same thing. So we'll go to LT spice. Just a minute. So this is spice now. This is the same circuit what we shown just back. Now okay, this is the circuit, and the same thing is realized in this LT spice. So this R2 and C1 will decide what is the 0 position, and of course R1 parallel with R2 will decide what is the pole position along with the value of C. So let us run this and then try to see the initial slope will be 0 dB per decade, and then it should go positive, and then it should again become 0 dB per decade. And the phase will be always plus, and that will be at 5.02 maximum at plus 54 degrees. Okay, let us see here. This is the magnitude plot. If you can see here, this is magnitude plot. This magnitude of almost minus 21 dB depends on what is the values of R1, R2. If you observe that transfer function, the magnitude of this is the magnitude. So whatever you have it as R1 by R1 plus R2 happens to be the DC gain. So DC gain is almost, since you have this as 100 ohm, this as 1K, it is 100 ohm divided by almost 110. So it's almost 1/10. So 1/10 is 0.1, which happens to be almost close to minus 20 dB. So this is what is the 0 dB gain. Initially it is 0 dB per decade. When I say okay, this is the DC gain. DC gain is almost minus 20 dB. The slope of the plot is 0 dB per decade. So we're going to have the first 0. 0 is located at 1.59 kilohertz. That's why the slope increases. And then there is a pole located at 15.9 kilohertz. That's why the slope again becomes 0. So first a 0 and then a pole here. Because 0 is located first, we're going to have the positive phase. The phase will be close to plus 54 degrees at a frequency of close to 5 kilohertz. You can just go down here and then try to see what the phase at 5 kilohertz. So you can see this is almost 56 degrees. So phase is almost 54 to 56 degrees, which is positive at a frequency of 5.02. So which is again decided by the values of location of poles and zeros. It is under root of fp into fz happens to be the frequency at which maximum phase of 54 degrees will occur. If you change the values of fz and fp's, the maximum phase will also change. So if I change the frequency of this, you can see if I make this equal to 100 now, if I make this equal to 100 and start simulating, because this 100 will affect both the zero frequency as well as pole frequency. Now the zero frequency will now become equal to how much? It will be around 15 point something, whereas the pole frequency will become, so this will be coming in parallel with, which will be almost 50 ohms. So 50 ohms into 0.1 microfarad. You can see this will move, this will also slightly move to right side. So both will move to right side. You can see both have moved to right side. This is almost close to 10 kilohertz, and you can see this is moved to almost this is whatever 50 ohm multiplied by 0.1 into 2 pi 1 over that will be the frequency. You can see phase also has changed to almost close to 20 degrees now, because your FP and FZ changed. That phase you are not getting that much phase as in the earlier case. Suppose if I retain this to 1k and if I make this equal to 1k, again the zero frequency will be there at 1.59 kilohertz, whereas this will be further reduced. You can see this will move to, you can see now it just went back. So now this has come back here. So instead of having it at 15 kilohertz, now it's at a lower frequency. So this way we can able to get the required phase at the required frequency using this type of phase lead network. Why it is phase lead means because of this values of or the connection of R2 in parallel with C1 will result in a 0 coming first rather than a pole. So in the previous circuit you might have seen that there is a pole which is coming first and then the 0, which was the lag network. The phase was also negative, but in case of phase lead network, so the phase of the overall signal will be positive compared to the incoming signal. So this way we can able to design any circuit for the required amount of phase lead or lag depending on the application. We'll see in the next video an all pass filter which will have a peculiar characteristics in terms of frequency response.